Hello, fans of geometric methods. We have a great tutorial on finding forms for the Xena form, including the cladding, which could be cladding or it could be structure. We'll talk about that. But most importantly, the two rules that are absolutely necessary and the fact that there really are no rules other than the two rules. Okay, how do we typically begin? Typically, I like to begin in plan view, looking down from bird's eye view down onto the horizontal plane, which is XY. Remember, Z is up in software and in life. So here I made a radius, a base radius. I called it 14.2 just to show you that you have control over it. And where it intersects the X and the Y axis establishes 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock. You don't have to do that, but it's nice to have something controlling the footprint. Then immediately put in the scale factor. This is a 6 foot tall pink human. And notice that might immediately help you make some decisions about something as basic as the footprint. So far, I have not touched any rules. None of these are rules. You could hit the X and Y axes. You could put points on these axes and just grab them and it's glued, excuse me, points on that circle and grab them with your mouse. And it will establish an infinite variety of landing points onto the ground. You could create another circle. You could create a square or a polygon or a triangle. It doesn't matter. None of these rules matter. Simply plopping down a point on the ground plane is actually also okay. It's just harder to control precisely with a single slider. You got to move around the foot of the strut. The most fruitful thing that I've done is this type of technique. So I'm going to ask you to do this initially in the studio, but you don't have to do this, and maybe you'll come up with something better. I have four spheres, each of which are centered on those four north, south, east, west points. Okay. I use symmetry so that 3 o'clock and 9 o'clock have the same radius, 12 o'clock and 6 o'clock have a different radius. You don't have to do that. You could have four different radii. You could have one radius, whatever you want. Then I like this fifth sphere being centered on a hanging point, and I'm calling that hang point, and that is glued to the z-axis. It doesn't have to be glued to the z-axis. It could be at the origin, could be sliding up the z-axis, or even cooler, it could be sliding on some inclined axis, right? But it's giving you some control with the placement of the hang point, either at the origin or sliding along an axis, and it doesn't matter what the axis is, and it controls the radius. So far, no rules, right? We're just playing. And the whole point of this exercise is that you get an arrangement of points. Now, occasionally a student will say, can't I just come up with an arrangement of points like this? And the answer is yes, you can, but there's very little control. In fact, I would argue there's probably no control over something like that. And in fact, I think it's harder to do that because you have such a blank slate that you don't know where to begin. How do I create a beautiful, interesting, visually striking three-dimensional spatial structure? I don't know how to do that. I'm not an experienced designer, right? So I'm giving you a tool that is infinitely variable and it doesn't prescribe to any rules. But the whole point of that first couple of slides is to get an arrangement of points in space that are controllable. And then you want to start lining up the struts from the foundation to the floating points. From the foundation to the floating points. And how you do that really does matter. So let's go through this carefully and ensure that we understand philosophically what we're doing. We're getting a visually interesting arrangement of points. but it has to become architecture at some point. So we have to control it and we have to make it reasonable. And that is a combination of aesthetics and program and structure. So you can start to see the outline of the struts that I put in. They're going from the ground up to the floating point, down to the ground, up to the floating point. You can color code your spheres. Here I have rad 2 centered on base point 2, rad 3 centered on base point 3. All of that is worthwhile doing. I color coded the spheres so you could really see which sphere is which. You don't have to do any of that. I'm just giving you some ideas. But now you need to start creating some architecture. Notice we were at the 15 to 20 foot radius of the space, if you want to think of it as a circular footprint. And now we have rule number 1. Rule number 1 is very important. You must start by stabilizing a single point that is floating. So here I arbitrarily chose to stabilize point P12. That is accurately named. It is the name of the intersection between sphere 1 and sphere 2. And that circle is circ12. And that magic point where that circle intersects the inner sphere, which is either hanging or it's on the origin, that establishes P12. So I just decided to stabilize that point. And here I got this big black strut that you can see, okay? And then, you could do other things. This is not recommended. I even suggest using this as a counter example. So here I have a series of floating points, but I just stabilized 4 of them with tripods. Technically, it's correct. Technically, it's very correct. Visually, I think it lacks vitality. I think it's kind of a dead end. You might not want these legs shooting out on your architecture, right? That you might want some drama of a little cantilever where the people are walking under it, or maybe it's a sunscreen. These struts out here can become programmatically and visually obtrusive, but technically it's correct. Now notice what I did on this example here. I have some floating nodes on the interior and I supported them with green struts. And this is rule number 2. Rule number 2 is that you must start building off of a previously stabilized node. You must start building off of a previously stabilized node. So these 2 nodes in the back are completely stable, as are the 2 nodes in the front. They're as good as the foundation. So I have a strut starting from there supporting the new node. Each new node requires 3 struts because of the essential 3 degrees of freedom that it has in 3D space. It's a point moving in 3D space. And then I had one more node here. I think you could see it, the actual hanging point. I'm using that, might as well. So here I suspended that, supported that, or it suspended that. It could be below the roof. It doesn't matter. With blue, if it was hanging below the roof, these struts would be in tension. If it's above the roof, those struts are in compression. Again, you need 3. And here I'm using rule number 2. Nicely, I have 2 struts going to a floating node. And I think not each, but 2 of those struts land on previously established or previously stabilized nodes. You could see them here. So that's a nice use of rule number 2. The base footprint circle, remember how we started? That can change and everything gets updated, but each of these images has the identical kit of parts. They're all the same sticks, they're all the same lengths, nothing changes, but you have an infinite variety of forms. And none of these are artistic. I'm just showing you the basics, right? Now we begin triangulating, and we have 2 reasons for doing so. One is that we're making architecture, so it has to provide some shelter. So this could be just a protective weather barrier, and we call that cladding, Cladding. It could be glass, it could be masonry, could be particle board, OSB, insulation, windows, anything. Or it could be structure. It could be a load-bearing element where we wouldn't even need the struts, which is it becomes a shell or a folded plate. And as the folds become more and more continuous and gentle, it becomes a shell. But it's a folded plate structure, which is a spatial structure, right? Or a surface active structure. The surfaces become the form. So either way, for us in this studio, it's cladding essentially, but we could talk about it as structure. So any triangle is impossible to warp. If you choose a hyperbolic paraboloid, you could do that with straight lines, but not with a solid triangle. And immediately we have something that looks visually interesting and is infinitely malleable. Throw it in a Rhino, throw it into Blender, make it look fantastic. Um, Notice that there's a certain set of triangles that exist for a certain set of struts, which is a super cool topology question, Topology. Limiting the amounts of struts is something we're going to do in the studio so that we have reusable sticks. And then, of course, the next step is origami. I'm not going to require that, but how cool is this that you could unroll these surfaces, laser cut it out, and actually make your surface active form like that. And then, of course, you can repeat the process, go up to the next story with another hanging point, another set of spheres at the previous apex. And the only rule is rule number one, you start by stabilizing one of those new floating points. You must do that. And you don't have to go all the way down to the ground. It's a long, long strut, but I'm just showing it to you. Here, I didn't have a whole lot of choices because I don't want it to shoot across the whole building on the interior of the space. So I just decided to make a very, very long, nearly vertical strut. And subsequent points build off of previously established nodes. That's number two. Rule number two, if I have 8 floating nodes, I should have 24 sticks, not 23, not 25. So I'm going to ask you to count the sticks and then triangulate as you want to. Okay, so that's the whole method. I hope you come up with fantastic structures. Let me just close by saying I'm expecting greatness. That's all.